In this video, I wanted to explain the concept known as simple harmonic motion. A good example of simple harmonic motion is simply a box of mass m attached to a horizontal spring. This box has an equilibrium position which we can call x equals 0 according to the spring's natural length. However, the box can also be moved to the left or right, causing the spring to be compressed or stretched. When this happens, the spring will exert an opposing force on the mass. Hooke's law tells us that this force is equal to the negative of the spring constant multiplied by the displacement of the mass. This force is known as the restoring force, and it's what defines simple harmonic motion. A periodic motion is only considered simple harmonic motion if the restoring force is proportional to the negative of the displacement. There are a few important terms you'll need to know in order to characterize any example of simple harmonic motion. First, it's important to know that the maximum displacement in either direction is known as the amplitude. If we let the two alternate positions of the box that I drew previously equal the maximum displacement in either direction, we can say that at the rightmost position x is equal to the amplitude, and that at the leftmost position x is equal to the negative amplitude. When the box moves from negative a to a and back to negative a, this is known as one cycle. This is actually true anytime that the box moves a distance equal to twice the distance separating the two amplitudes. Another important quantity that you'll need to know is the frequency, which is simply just the amount of cycles completed per second. In contrast, the period is the amount of time that it takes to complete one cycle. You might notice that these are reciprocal quantities, so the frequency is equal to 1 divided by the period. It's often helpful to look at simple harmonic motion using the conservation of energy equation. We can write the total mechanical energy of this system as 1/2 mv squared plus 1/2 kx squared. This tells us that no matter where the mass is located, the total mechanical energy of the system is equal to some combination of kinetic energy and spring potential energy. What's important to know is that when the mass is at either of the amplitudes, its velocity momentarily becomes 0. This means that at that instant, the total energy of the system is entirely potential energy. Similarly, when the mass is at x equals 0, it's at its maximum velocity, and there's no energy stored in the spring. This means that the total energy at that time is entirely kinetic energy. We can then say that at x equals 0, the total mechanical energy is equal to 1/2 multiplied by the mass multiplied by the maximum velocity squared. Similarly, when x is equal to the amplitude or the negative amplitude, the total mechanical energy is equal to 1/2 multiplied by the spring constant multiplied by the amplitude squared. Because the total mechanical energy is always conserved, we can say that the following equation is also true. Simplifying the equation to get v squared and then plugging in x equals 0, we can find that the maximum velocity is equal to the square root of the spring constant divided by the mass multiplied by the amplitude. Simplifying the velocity squared equation, we can see that the velocity is equal to the maximum velocity multiplied by the square root of another term. This allows us to say that the velocity of the mass at any point in its motion is equal to its maximum velocity multiplied by the square root of 1 minus the displacement squared divided by the amplitude squared. In many situations, you'll also need to calculate the period and the frequency of the simple harmonic motion. These can be found using the following two formulas if the mass and the spring constant are known. Notice how these quantities are both independent of the amplitude. I won't show the derivations here, but these two equations are both derived from the fact that the displacement versus time in simple harmonic motion follows the path of a sine wave. If you're interested in this derivation, you can visit my website linked below. Because of the sinusoidal nature of simple harmonic motion, the displacement at any time can be found using the following equation whenever the amplitude and frequency are known. If you still have any questions on simple harmonic motion, feel free to comment below and I'll do my best to answer them. In addition, you can visit fastphysicshelp.com for more information on this topic. If you found this video helpful, please give it a like and consider subscribing to the channel for more fast physics videos. Thanks for watching.